Greetings, good morning or good afternoon, depending on where you are. My name is Professor Duke Orata. We are continuing with our lectures in thermodynamics, and I continue encouraging you to look at these lectures so that we build up systematically. Today we want to look at convection, heat transfers where we have phase changes. So we want to look at that particular concept, convection. Phase change. Traditionally, we have talked of three phases or states of matter, that is solid, liquid, and gas. And so we can have a solid being converted to a liquid, of course, through a process. You either heat it up and converts to a liquid in a process which we call fusion, or melting. And then, of course, we have that process where the liquid can go to vapor, and that process is called vaporization. Vaporization. And you can have a third process where you can have a liquid go directly, a solid go directly to to gaseous phase or to vapor in a process which we call sublimation. Let's just remind ourselves there are three states of matter. That is solid, liquid, and gas. So if we have the transformation, that is, you can have solid going to liquid. This particular process is fusion. So the enthalpy change accompanying that process is normally called delta H fusion or DH fusion. And we can have liquid going to the gas phase in a process which we call evaporation or vaporization. The third phase can be where we have the solid going to gas, and that process is called sublimation. These phase transformations for these particular processes are normally accompanied by release or addition of energy, so that when you have the reverse process, for example, gas going back to liquid, that is called condensation. Liquid back to solid, that is freezing. And if you look at lectures which we've done in phase equilibria, these boundaries of these phases are actually determined by the Clapeyron equation. You can construct these boundaries by use of Clapeyron equation, which is delta H by delta V. Very, very important for us to remember that. And that entropy change, remember, based on Clausius inequality, what we call Clausius inequality, ds is greater or equal to dq, ds greater or equal to dq over t. So under constant pressure, the heat transferred under constant pressure is the same as dH. And again, this is a very important quantity which you need to remember. This is a thermochemical observable because heat is a path function and H is a thermodynamic state function. So this is a link between a thermochemical observable and a thermodynamic state function, which is very critical in thermochemistry, which is a very important concept in determination of some of these energies. So in place of delta S, we can put that dP by dt by dt will therefore be dH over T dV. This is Clapeyron equation, and it's very important in the construction of these boundaries involving phase transitions. So what are we saying? In a nutshell, when you have industrial processes, for example, industrial processes involve heat transfers. And in these industrial processes, there are normally possibilities, or there's normally a very high likelihood of a phase transformation. There can be evaporation, that means liquid going to gas, or there can be condensation, that is gas going back to liquid. So for industrial processes, the heat transfers can involve phase transformation of the fluids. With example, we can have evaporation or condensation. We are basically solid, it's liquid, to gas, evaporation. The reverse reaction is condensation, because that is gas. Very important. Now, suppose we look at condensation on a laminar film on a vertical wall. Consider condensation in a laminar film, a vertical wall. So, let us just draw a schematic of that profile which you expect. Schematic. We have our vertical wall. Call that X. And that's Y. We'll have here, we have vapor. That's the temperature, the wall. Let's call this the saturated temperature. Saturation temperature. Here we have the vapor. So this vapor will condense in the laminar film. And when it condenses in the laminar film, so the vapor condenses in the laminar film, vapor condenses laminar film. So what happens? It will lose heat. It will lose heat so that its temperature will tend towards being lower than that of the saturated temperature. It will lose heat to the wall, lowering its temperature to below the saturation temperature. And of course, the liquid elements in the system will either move downwards or upwards. In other words, they will move parallel to the vertical wall, either downwards or upwards, and the forces which will be causing these movements are not hydrostatic pressure, as we have seen in other cases, or inertial forces, but rather it will be a combination or a complementarity between viscous forces and gravitational forces. The liquid elements will move upwards or downwards along the wall, parallel to the wall. And we have seen this particular schematic. Let's just put the streamlines. This is the film. Now, let's just write what we have said in terms of, so we have said that the movement of the liquid elements is not due to hydrostatic pressure forces, or inertia forces, but rather a complementarity of viscous and gravitational forces. Now, if we know that is the case, because remember there will be no temperature, there will be no temperature difference at the film, the condensed film surface. There will be no there's no temperature difference between the condensed film and the vapor. So we don't expect heat, for example, to be transferred from the condensed film to the vapor. No. The film surface to the vapor. No, because the temperatures are about the same. So because the temperature film surface and that of the vapor are about the same, there will be no heat transfers between the two. Be no heat transfer. Remember, there is no temperature gradient, therefore we don't expect that. Now, if we look at some unit element in this system, let us say, let's have another schematic. This is X. There's no viscous, the shear, so we assume as 0, and we are assuming at the top of the vertical wall, the thickness is 0. Sigma is 0. And so if we take some unit element here of height dx, or that height dx, unit element of height dx, and of course it says that's our velocity profile. Let's say this is our velocity profile, and the thickness here now, let's say sigma. The thickness is sigma. So we are looking at this element there. So let us say that we have that amount of liquid that volume element is dm. So that we have m, that will be m plus dm. Now, this is our wall, don't forget. That's our wall. And of course, remember the thickness. The thickness of this layer here, is because of condensation of vapor, not because of retardation in terms of movement. It's because of condensation of vapor. That's very important for you to note. Because if there was retardation, then there's also a possibility that that can happen. So the thickness of the layer, sigma, increases as a result of vapor, not retardation. Associated with fluid flow. It's very important for you to note that. Very important for us to note that. And so, what are we saying? The heat the heat which is transferred from condensation of vapor, because remember, when we have the first transition from liquid to vapor, there's an enthalpy change, there's energy change associated with that. And there is also energy change associated with condensation. Heat is released as a result of that condensation process. Remember, note that the processes are basically assumed to be occurring under constant pressure. And therefore, the temperature is relatively constant. Always remember that. The temperature is relatively constant. So if the heat which is transferred, it will not be parallel, but it will be towards the wall. Remember, the streamlines are parallel. To the wall. So the heat which is transferred will be purely by conduction, and it will be towards the wall. So the heat transferred as a result of condensation will be towards the wall. It's purely by conduction. And so, we can therefore evoke Fourier heat laws to see how we can compute the heat transferred, the rate of heat transfer in that process. Therefore, to compute the rate of heat transfer, we'll apply Fourier's law. And we know that the rate of heat transfer, Q, we can say is minus K dx, talking of that unit element, dy, and that is equal to minus H dx of theta dx of Ts minus Tw. Remember Ts, because at the wall, S is the saturation temperature. And so we already have good idea what we're talking about here. So we don't need it. We believe now it's in mind. So we have, if we rearrange these quantities, then minus k dx into T s minus Tw. The dy is the thickness of the boundary. We have already seen that in many of the lectures. Minus h dx ds minus Tw. Of course, we can cancel out quantities here. Cancel out that quantity with that. Can cancel out the x. So we have minus k over sigma is equals to minus h, or k over sigma is simply h. And so we can write it in terms of dimensionless quantities. That's the Nusselt number. In terms of dimensionless quantities, that's the Nusselt number. Remember that? Then we know that the Nusselt number since the Nusselt number is HL over K, so we just multiply both sides by L over K, then you get it in that configuration. Multiplying by L over K, we get K over sigma times L over K, that equals to H, that will now be H L over K, and that's the Nusselt number. So the K's will cancel out, so the Nusselt number will simply be given in terms of the K's cancel out. So the Nusselt number here will be given by L, which in our case now is X, L over K, or X, L over sigma, or X over sigma. And so, one point to note is that most of the chemical processes involving heat transfers, they are accompanied by phase transformations. And those phase transformations are very important because those phase transformations, as there is a phase transition, there is changes in energies in terms of associated with those phase transformations, called them enthalpy changes. The various, sometimes to refer to them as latent heat, and so forth and so forth. Some are even the values are all tabulated, and somebody can access and know what are the associated energy changes. Number two, it's important for us to note that when this condensation takes place in this laminar film, while it moves up and down, can move up or down, most of it will be because of viscous gravitational force as opposed to hydrostatic pressure or inertial forces. Very important for us. And we have seen that we can actually, we know that because of the streamlines, when there's condensation, that heat will be transferred to the wall. And so we are able to use Fourier's law to be able to compute the rates of heat transfer and further be able to convert them into dimensionless quantities and see how they are. So we will be moving next time to calculate this boundary, the boundary thickness and so forth in our next lectures.